Okay, let's get into surface integrals. So we're going to start off talking about surface area, but we've already done this. So I'm not going to spend a ton of time, but I am going to kind of recap it. So basically surface area, if we have a surface in 3 space, we want to be able to find the area. So we talked about this. We even did an example last time for a parameterized surface. You had to do it for that paraboloid you had. So this will do the surface area of a parameterized surface. The advantage of this formula, and I can't stress this enough, if your parameterization is correct, everything else is just a matter of following the procedures. Okay, what does it say to do? Well, it says to take the partials of your parameterization with respect to u and v, do the cross product of that and take the magnitude, and your limits will be the exact same limits you had to use on u and v to create your parameterization. All right, so that's what we spent time doing that last time. If you can create the parameterization in Calculate 3D that makes the surface you want to make, you can do the surface area because it's just a matter of doing the partials, cross product, and setting up and calculating your integral, which if you're using technology should all be very straightforward. So let's talk about doing a cone with a height of 1, just a basic 45-degree angle cone, which would have the following parameterization. So this is where I'll switch over to Maple. And so, like I said, first thing you do, make sure you have the correct parameterization by plotting it. So I put in my parameterization. So that's my vector for parameterization. I'm calling it u instead of r because I'm using r and theta instead of u and v. But then plot it. All right. That's the cone I expect to see. It's got a radius of 1. It's got a height of 1. So I now know this is my r. This is my position vector. And here are the limits on my definite integral. All right. So now we go back to the formula. Formula says we take the partials, one in my case, one with respect to r and one with respect to theta. And I do the cross product of those to get, and the magnitude of that is my integrand. So again, I'm going to do that in Maple just because I don't want to spend the time. So that's what this command here is doing. Right here, this is taking the derivative or differentiating with respect to r. This one's differentiating with respect to theta. All right. So that's what we would get if we do those partials. Then we do the cross product of these two vectors. Again, stuff we've done before. Now, Maple doesn't always do a nice job simplifying this last one here with the cosine squared and the sine squared. That would simplify down to r. So if we were doing this by hand, we would just have r in this last one. And so now we can get the integrand by taking the magnitude of this. Well, if we take the magnitude, it's the sum of the squares of the components. That's going to give us another cosine squared plus sine squared. So we'll end up with an r squared here plus another r squared. So basically, we end up with the square root of 2r squared. So I want to keep track of that because we're going to use this one again. So for us, again, I'm calling it u sub r because of the variables I used. Crossed with u sub theta. When I do the magnitude of that, I get square root of 2r squared or square root of 2r. That's what's going to go right here. That is my integrand. And again, now because we do it via parameterization, the limits on our integral are the limits for our parameterization. So it's going to be from r is going to go from 0 to 1, theta is going to go from 0 to 2 pi. And there's my surface area. Same thing we would get if we calculated this out. All right, oops, we kind of passed it. Pi times square root of 2. All right, we did this last time. This part's not new, but because we're going to build on this, I wanted to revisit it. Okay. So again, when we're doing via parameterization, the hardest part, the work you're going to have to do is creating the parameterization of the surface, because everything after that is straightforward. Everything, even with the surface integrals. And we'll talk about that when we get to it. Okay, questions about that first example? Like I said, there's a PDF with all these examples executed too for you. And I think I linked it. Let me see it. Yeah, and I linked it to the calendar too, so you can find it even easier. So you can follow along with that or revisit it later when you're working on some problems. Now, we also talked about surface area if our function is given as a function of x and y. All right. So we might have a position vector that's given in terms of x, y, and z, but z is a function of x and y. So we would think of it as x, y, f of x, y. And then doing the cross products, basically we get the following. The square root of f sub x squared plus f sub y squared plus 1. Again, this is something we've seen before. So to do the surface area, if we're given a function of x and y, we do the following. We did this problem before as well. So again, not going to spend a lot of time on it. We would find f sub x, f sub y, plug them into the formula. And then we would find out what this looks like in the first octant, just like we did with double and triple integrals. We would find that region in the xy plane, which is a triangle, to create our limits. So that's an example we've done before. So here I'm just going to run through it with Maple. We're doing that function. All right, so there is our surface. And this is our region in the xy plane right there, that triangle. So we get 3 square root of 14 would be the surface area of that piece of the plane. Again, not a new one, but because we're also going to look at surface integrals in both forms, I wanted to revisit surface area, because surface integrals are just integrating a function over the surface area. So we're literally just putting a function in front of these. All right. So that was the old stuff. That was a bit of a review. Let's move on to the new stuff. So surface integrals. So what are we talking about with surface integrals? So now so if you think about what we were doing with double integrals, we were integrating over a region in the xy plane. Surface integrals allow us to integrate over any two-dimensional surface. It's no longer restricted to the 2D plane. That's the biggest difference. So, for example, if if the function that we're integrating over was a density, then what we would get as a result is the total mass of that 2D surface. Just to give an idea of what we're looking at with surface integrals. So first thing we're going to talk about is surface integrals over a function. So again, notice that the formula is basically what we had before, right? Here's this part with the function put in front. So calculate the surface integral of the function xy over the cone of radius 1 from the previous example. And I did put it in the first octant, so we wouldn't do the whole cone. We just adjust our limits on theta for that. But remember, this is what comes from this cross product here. So the only other thing is the xy. It has to be converted in terms of our parameterization. Let's see. I didn't put the parameterization on there, but our parameterization for a cone was U equals our cosine theta, our sine theta, gamma r. Okay, that was the parameterization we were using. And we had theta going, if we're doing the whole cone, theta is from 0 to 2 pi. If we're in the first octet, it's 0 to pi over 2. Not a big deal there. But here's another thing that we need to do. We can't put x and y in there and expect to calculate this because we're calculating over our parameters. So our double integral, the x and the y, we have to sub in from our parameterization. In other words, this is x, y, and z. So any x's are going to get an r cosine theta. The y is going to get an r sine theta. And we didn't have a z in here, but if we did, it would get an r. And then we still have the magnitude of our cross product, which is rad 2r. And then whichever order we want, dr, d theta. R is going to go from 0 to 1. And if we're doing the first octant, it'd be 0 to pi over 2. If we were doing the whole cone, it'd be 0 to pi. All right. So what I want you to, the reason we're doing this is I want you to look at this as just adding a layer to surface area, right? If you can do the surface area, you can do the surface integral because all you're doing is taking the function and putting in your parameterization. Everything else stays the same. This is all that got added in from doing the surface area. This was that function xy, just with our parameterization put in. So everything kind of just layers up from surface area. So again, I'll do it with Maple, and I'll kind of, like I said, I'll talk you through what everything's doing. So here I'm putting in the u, I'm putting in my function, and I'm taking the partials, udr and ud theta. I'm just doing it all in one line. Here I'm subbing in the parameterization into the function. So instead of it being f of xy, it's going to be f of x of r comma theta, y comma theta. And z comma theta if we had one. All right, so that's the x times y. I plotted these together because I wanted to show you that, you know, when you're doing a surface integral, think about what's happening. You're integrating a function over another surface. There may not be a visual representation that makes sense between the two. Okay, so if you see, this is our cone, and then this is the xy function. There's nothing going on. There's nothing to see there. So really, from a plotting standpoint, the only thing we care about is that we get our surface parameterized right. Past that, we don't care what the function we're integrating over looks like, because there's nothing visually going on there that's going to give us any information. All right, so this is just putting together the integrand. Again, Maple didn't simplify, but this is that square root of 2r. And then here's our surface integral. All right. So again, I want you to look at this as layers. We've done surface area before. Now all we're doing is putting a function into our surface area integral. So that was for parameterization. Questions about that? Okay. So again, I think what you're going to find depending on the problem, one of the hardest things is if you have to come up with the parameterization for your surface, and we'll get to practice a couple of those with the worksheets. Past that, it's just putting things in the right place. All right, back to the slides. Now, if we're going to do surface integrals of parameterization, we have to do them for functions of x and y. Again, This isn't going to be mind-blowing. Right here, this was the same piece that was in the surface integral. All we're doing is adding in the function. It's just, it can't be of 3 variables because it's only a double integral. So instead of being of x, y, and z, we're going to let z, whatever the function is, we're going to replace any z's in there with that. All right. So let's say we want to find the surface integral of the function x, y, z over this plane. Well, that part's easy. We've done that part before. So let's start with that. That part is just going to be square root of f sub x on this one is -3. So -3 squared. F sub y is -2 squared plus 1. So that part would have been already in our surface integral. And the only thing we have to add is the function, except we can't have z in there. But we know what z is equal to on this plane. So we would have x, y, and then our z is 6 minus 3x minus 2y. Over our region, which is the same region that we had in the last one. The limits are actually even going to be the same. So again, all we did was add a layer, which was now we had to integrate over the function. We just can't have a z in there because it's a double integral. But that's okay. We know what z is equal to on this surface. Questions about that setup? Doing the limits would be the same as doing the limits for the surface area. What we're looking at is that rectangular region in the xy plane, which comes when we set z to 0. Basically, we get 3x plus 2y equals 6. That's what's going to make that triangular region. And we're back into what we were doing back in chapter 14, right? We're doing double integrals. You know, we decide if we want to do x first or y first, so on and so forth. So I really am trying to push for you guys to see how just everything is just built off of what we've done before. Double integrals, we've done those, right? We know how to find regions for those. We've done parameterizations. We've done surface area for both parameterized functions and functions to variables. So all we've added so far is some function that we're integrating over. And all we do is put that in the surface area formula. We just have to put in make sure it's in the right form. If it's a parameterization, we plug in our parameterization for x, y, and z. If it's in terms of x, y, and z, if it's as a function, all we do is we make sure, okay, if there's any z's, we plug in the function for it. And there are going to be problems that you can actually do either way. You know, when we'll look at a couple later, we'll do them one way and then we'll do them the other, just to see if we get the same thing. Okay. Questions about that example? All right, so what we've done so far are what are called surface integrals. And what we're doing is we're integrating a function over a surface. Very similar to what we were doing back in module 4. When we were doing double integrals, we were integrating a function over a region in the xy plane. The difference is now that surface doesn't have to be in the xy plane. It could be some paraboloid, or it could be a sphere. It could be some more complex surface. It's not restricted to the xy plane anymore. That's the biggest difference. And that's what's adding this part here for this one, or this part here. Okay. So those are surface integrals of functions over a surface. The other type of surface integral we need to talk about are of vector fields. We've talked about these a little bit already when we looked at Green's theorem, because flux integrals are a form of a surface integral. So we've actually been introduced to this concept already. So let's talk a little bit in general about surface integrals over vector fields. This is where things start to get kind of fun. There's a lot of really cool stuff that we can do with this. So we've talked about vector fields, right? We talked about them being force fields. We've talked about line integrals. We talked about them, doing work as a particle moves along a path. We talked about them if they represent a flow of a fluid. So what makes a flux integral is how much of that fluid, if we're looking at a fluid, is going through a surface instead of with a surface. So if you remember when we did line integrals, we were interested in how much was going with or against the vector field. Now we're interested in how much is going perpendicular to the vector field. And that's the idea behind a flux integral. So again, we've already encountered this concept of flux integrals when we looked at Green's theorem. So now we're going to get a little more in depth with it, with this idea of surface integrals. So surface integrals are a transfer of something, fluid, particles, energy, across some surface. So let's take a case where we can kind of imagine what's going on, right? Water flowing through a surface. If the water is flowing perpendicular to the surface, a lot of water is going to flow through the surface. The flux will be very high. If the water is flowing parallel to the surface, no water will go through the surface, or little water, and the flux will be very low. And that's the complete opposite of the line integral, right? If the water is going perpendicular to the path of the particle, then we get a line integral of 0. If it's going with it, we get a large line integral. So basically, we're adding up the component that is perpendicular. So I'm going to go through how we get to a couple different formulas for flux integrals. Again, you do not have to know how to get to these formulas. You just have to know how to use them. So what we care about is the normal vector to our surface. We've talked about normal vectors, right? One way of finding a normal vector is the gradient. So the gradient's going to come up again. And so because what we're doing is we're looking at a vector projection, we're going to do the dot product of our vector field with the normal vector, because we want to sum up the components that are perpendicular, or whatever component of each vector that's perpendicular. So this will give us that total flux of the fluid or whatever it is going through the surface. So if it's in the direction of our normal vector, it's positive. If it's opposite the direction of our normal vector, it's negative. And we'll talk a little bit more about that because for any given surface, there's two normal vectors, right? If you imagine a surface, there's going to be one going this way and one coming this way. They're 180 degrees opposite of each other. And we're going to have opportunities to choose which normal vector we want to choose. And we're going to talk about that a little bit as we dive into this. All right. So we know that cross product, remember, this is going way, way back. We're almost at the end of the semester, this is going back to the beginning of the semester. Remember what the cross product gives us? It gives us a vector that is perpendicular to the plane that the other two vectors lie in. So this gives us a normal vector. Now we can simplify this a little bit when we add in the f dotted with the normal vector. And again, this is not something you need to know. I just want to show you where it comes from. The normal vector we could get by doing the cross product. Well, those magnitudes are going to cancel. And so this simplifies our work. Now, notice the form that this formula is in. This is specifically if we have a parameterized surface. So if we have a parameterized surface, we can do the dot product of our vector field with our parameterization plugged in with our cross product. Okay, so let's do an example to kind of help bring this home. So let's see, I'm gonna need some board space here. All right, so we've got a paraboloid, and like I said, I'm doing this one in terms of a parameterization. So we need to parameterize our paraboloid. So I just want to make sure I use the same one that I used in here. Okay, which is I think the same one that some of you guys had last time. So a parameter, there's multiple form parameterizations for a paraboloid. There's always going to be infinitely many. A very easy one is u cosine of v, u sine of v, and then u squared to give that that paraboloid. Okay. Now, two things have to happen here. Number one, we're going to need the cross. We're going to have to find our partials and take the cross product. I'm going to do that in Maple because that's not new for us, right? I'm going to find r sub u. That's the derivatives with respect to u. I'm going to find r sub v, and I'm going to cross product those. Not find the magnitude this time. I'm going to leave it as a vector. All right. But again, this is stuff you guys have done before. The other thing we need to do is we need to get f. Well, we know f is 0, negative yz, but it has to be done in terms of our parameterization because we want our integral to be in terms of u and v. So f in terms of our parameterization would be 0, negative u sine v u squared. All right, because that's our x, y, and z. Sorry, this marker's u diagonal. All right. Okay, questions about that so far? So again, mechanically, what we do, find r sub u and r sub v of this and get their cross product. Then we take our vector field, plug in our parameterization, and then we'll take the dot product of those two things. That gives us our integrand, and our limits are the limits on our parameterization, which I should have included. Let's see, v is going to go from 0 to 2 pi, and u is going to be from 0 to 1. I think it was just a paraboloid of height 1. Those are going to be the limits on our integral. So again, once we had the parameterization, everything was just algorithmic, right? Just step, 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 step. All right, so put in my vector field, put in my parameterization. I'm going to take my partials and find the cross product. Once again, Maple didn't simplify this. This last one would have, if we were doing by hand, we'd simplify down to a minus u. And then I've got to put my this here, the substitute command. I'm putting in my parameterization into my vector field because I don't want it to be in terms of x, y, and z. So that's this one right here. The integrand comes from the dot product of those two. This isn't the most, if we were doing this by hand, it would look a little more simplified. And then we have the double integral, and you'll see my limits are just the same limits on my parameterization. All right. and I got negative pi. So again, now negative pi tells us that the flow of whatever this is, fluid or whatever the vector field was representing, is going in the opposite direction of the normal vector we happened to choose. All right, so we need to talk about that a little bit because that makes a difference. Because when we did the cross product, we found a normal vector, but we could have found one 180 degrees in the opposite direction by changing the signs on all the components. All right, so I used this normal vector here, but if I multiplied this normal vector by a -1, I still have a normal vector. And everything still stays true. So we do have to think about, okay, well, geez, that makes a difference. How do we decide which normal vector to use? And it is a lot of times going to be context dependent. All right, so it seems like I'm avoiding the answer, but unfortunately, that's kind of the truth of it. So let's talk about that a little bit. Should it be positive or negative? Well, that would have depended on which normal vector we would have chosen. So, like I said, every surface is going to have two normal vectors. So the set we choose determines the orientation of our surface. So a lot of times we choose it in a way that makes sense for our context. And I'll talk about a convention here in a second. But there is a situation that gets a little wonky with surface integrals, for lack of better terms. And that is because the surface must be orientable, meaning that it does have to have two distinct normal vectors that are 180 degrees opposite of each other. And while you're probably thinking, well, what the heck is he talking about? If we imagine a piece of paper, of course there's two normal vectors. Or if we imagine any of these surfaces we've looked at, there, the paraboloid, of course there's two normal vectors. Well, then we'll look at the counter example, which is the Mobius strip. All right. So if you think of a normal vector coming out of the board here, and it stays on this side. Now it crosses, now it's into the board, and now when it comes back around, it's going into the board. We swapped sides on the surface without ever actually changing over to this other side of the surface. So the Mobius strip is not orientable. It doesn't follow that definition of having two distinct normal vectors for a given point. Because if we start on one side and we trace all the way around, we end up actually on the other side, even though we didn't change the sign of the normal vector. So we need our surface to be orientable for this to happen. All right, so let's just talk one more time about this orientation. We don't have a ton of conventions for this. That paraboloid, what we would do is we would make a decision. We'd say, okay, we want our positive orientation to be going out of the paraboloid because we want to know how much of the gas is expanding outwards. Or we might want it to be inwards if, it's completely up to us to decide. And I don't want you guys to worry about that. Like, if you're getting a problem in the homework, it'll say an upward, downward, outward, or inward orientation. So if a surface is closed, there is a convention for it, but even this convention can be changed if it's to your advantage to change it. So if a surface is closed, like a sphere or something like that, then typically the positive orientation would be an outward orientation. Think of a gas expanding. But again, it doesn't have to be. It's just kind of a convention. There's no logical theorem or premise that requires it to be true. And I only spend so much time on it just because I want you guys to be aware of it. It's not a big deal. It doesn't completely mess up your integral, but it does change the sign on it, right? It'll make it positive if it's negative and vice versa, but the magnitude will be the same. And it's always something you can change later. If you say, well, I would have rather had an upward orientation on this surface, all you got to do is change the sign on your final answer. So it's not a big deal, but it is something we have to be aware of. Okay. A couple more examples I want to do before we go to try some. First off, we did a surface integral over a vector field or a flux integral with a parameterization. We can do it with a function as well. How does that look? All right. Well, we looked at this form. F dotted with a normal vector that came from the cross product. All right, great. Well, really, that's all we need is F dotted with a normal vector. So another way of getting a normal vector, let's say our function is given in terms of x, y, is via the gradient. So nothing new, right? So F dotted with the gradient. So let's do that example we just did. What do we got? We got negative pi, right? Let's do that exact same one. So let me just, this is me just, shoot, I forgot to put it on there. Okay. Yeah, let's go back then. Do I have it up? I do not. Okay. I want to go back to, sorry, I put a new slide on there and I apparently forgot to upload it. This is our function. And so let's write this, let's just write this down and then we'll go back to that slide. All right, so our paraboloid, z equals x squared plus y squared. And our vector field is 0, comma, negative y, comma, z. All right. So now let me skip back ahead. Because now we want to do it as a function and see, like I said, there are some we can do either way. This will be one of them. So now we want to dot f with the gradient. But once again, we can't really have z's in there. So how does this work? Well, first off, we need a normal vector. So the first thing we do, we bring the z over to the other side. So I'm going to grab and see if I can find a little bit better marker. So first thing we'll do is move the z over to the other side. So now it's f of x, y, z. And this is always going to happen. You're always just going to have the minus z over here. And so the gradient of f is going to be 2x, 2y, negative 1. Okay, that's great because there's no z in there. Remember, this is a double integral. All right, so that takes care of the normal vector. The other thing we need is our f, except we don't want a z in there. So our f is going to be 0, negative y, and we'll substitute in what z is equal to, x squared plus y squared. So these are going to be the two things getting dot producted together. Order does not matter on dot product. You can do f dot gradient or gradient dot f. That's going to be your integrand. Okay. I'm going to do that with Maple. It's actually not a bad one. You can kind of see we're going to end up with what, 0. Let's go ahead and do it actually. It's really not that bad. 0 minus 2y squared. And then minus x squared minus y squared. Let's just write it this way. Which we can simplify, but I'm not worried about that right now. Okay, but definitely you guys would simplify it for sure before you integrate it by hand. Absolutely. Okay, last thing we need to talk about though, this time, now here's the difference. And this is another thing I want to stress. When you've done the parameterization, you've already found your limits of integration. We didn't do parameterization this time, right? We're doing it as a function. So we do still have to think about what our limits of integration are. Well, what is our surface? It's a paraboloid that has a radius of 1 at the top, right? So if we think about, that paraboloid here, well, what's our region of integration? It's that shadow region in the XY plane. So it's a circle of radius 1. So if we're doing, since I have it in rectangular, and this is, again, how many times have we done circles and spheres at this point, right? I know it's been a little while, but this is going to be a nice little review. This is -1 y minus square root of 1 minus y squared to square root of 1 minus y squared. And then -1 to 1 if I'm doing dx dy. I would, yeah, if we're doing this one by hand, we would almost definitely switch it to polar, right? Or if we're doing it in maple or symbol lab, we'll do it this way. But yeah. But that's, so again, I kind of want to stress the difference there, right? The work was at the beginning for a parameterized surface because we had to come up with the parameterization, but that got us our limits. In this case, there's a little bit of work at the end. Everything else was kind of easy. Gradients easy, dot products easy, but we have to think about what our limits are. And that goes back to that shadow region idea from last module. All right, let's see what we get when we calculate this guy. Which I'm pretty sure I have it in here. Let's see. Yes. All right, so there's our gradient. Maple's putting that E sub x, E sub y, E sub z. That's kind of like the IJK when we write it in that form. That's all that is. So don't let that throw you off. All right. I took the opposite vector, so I multiplied it by a -1 because I did this problem before and I know it's going to happen. There's my dot product, but I can't have the z in there, so I have to substitute that out. So there's the integrand, which is what we would have got if I would have finished simplifying. I got a little lazy there. And then there's our integral, and then there's -pi. Now, one thing I want to show you, because of how I set this one up, and I don't know why I put it in as z minus x squared minus y squared, but if I had not multiplied and I'm just going to run through the command so you can see exactly what would have happened. All right, so if I would have just kept it this way, I'm still getting a normal vector, right? But I get pi for an answer. Notice the magnitude is still the same. I just got the opposite sign. It's because I'm using the opposite normal vector that we used when we did it in the parameterization. All right. And what we would do is we go back and look at our normal vector, in this case, the gradient, the one that I used. So -2x minus 2y, 1. So I noticed that the z component is 1. So that tells me it's got an upward orientation. So if we were asked to use one with a downward orientation, we would want to make sure the z component is negative. And so that's why the negative was in on here. And we get the same, not just the same magnitude, but the same sign. All right. Again, it's not something that I want you to be overly worried about, right? It's not the hardest part of this. It's more just it's more of an awareness. Like, hey, there are two normal vectors. Did the problem tell me which one I should pick? Okay. Questions about that one? So that was nice because we got to see that one done 2 different ways. We'll do this next one 2 different ways as well. I know I spend a lot of time on this section, but I think it's worth it. And a couple things. All right, one more example. And there's going to be there's a reason why I'm going to do this example, because we're going to do this one again on Thursday with one of the theorems. So basically, let's say our surface is a hemisphere. And this is something that we actually talked a little bit of last time with the cone. Usually when we have like a hemisphere, there's no bottom on it. It's not a closed surface. So I'm putting a disk underneath, x squared plus y squared equals 1, to make this a closed surface. All right. So it's a hemisphere with a bottom. So if we want to calculate the flux, and we'll say that the outward is the positive orientation, because that's the convention for a closed surface. So we'll talk about specifically how we're picking which normal vector we're going to pick. So let's see what happens. Now we do have to break this thing into 2 regions. I'm going to do it first via parameterization. Remember, the parameterization for a sphere are the equations that are the transformations to spherical coordinates. Rho sine phi, sine theta, so on and so forth. So, or sorry, rho sine phi, cosine theta. Now I'm doing a sphere of radius 1. All right, so the x squared plus y squared plus z squared equals 1. So right here, I'm not going to put these up on the board. If you have questions, we can always take a look at them, but I'll tell you exactly what's happening here. All right, so I put it in our vector field. Here is, those are the transformations that we did these all the way back in module 2. X is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is cosine phi. It just so happens that rho is 1. And so our limits, well, we're doing a top half of a sphere. So we're going to go, theta is going to go from 0 to 2 pi. Phi only needs to go 90 degrees to get a top half of a sphere. So it's only going to go from 0 to pi over 2. So we already know our limits because we're doing the parameterization form. So think about what we do next. We find the partials of our position vector, right? We're going to find r sub phi and r sub theta and find the cross product. So r sub phi, r sub theta, cross product. Once again, Maple kind of drew this thing out because we do have a cosine squared, sine squared that would have gone away. And we want, excuse me, we want an upward or an outward orientation, right? So we want the z component to be positive. So we're going to leave this normal vector as is. We don't want this z component here to be negative. So this is the normal vector I'm going to use. Now, again, I know I'm doing the whole thing in Maple, but I can't stress enough. I didn't do anything that you guys haven't done. All I did was the parameterization for a sphere, took the partials with respect to phi and theta, and then did the cross product, not the magnitude of it, just the cross product. Because remember, this is going to get dotted with our vector field with our parameterization plugged in, right? So again, everything is just, oh, I've got my parameterization. Okay, then I go step 1, step 2, step 3, answer, right? And guys, you can absolutely use technology for this. Everything I'm doing here in Maple, you could do in Wolfram Alpha or Symbolab, just as easy. Again, the only reason I'm doing it in Maple is because we're doing 7 different examples. To have done those in one of those, in those programs, I'd have had a bunch of windows and it would have been a mess. So I appreciate your understanding. Okay, so here, all I'm doing now is I'm subbing my parameterization into our vector field. So that's the given vector field, that x, y, z squared, with our parameterization plugged in. The integrand is the dot product of this vector and this vector. Maple didn't simplify it as much as I would like, but that's okay. We would have had it looking a little cleaner by hand. Now, again, my limits, phi just goes from 0 to pi over 2, theta from 0 to 2 pi, and we integrate. And we get 11 pi over 6. All right, so that is for that top half of the sphere. Now, I also have to do the same for the bottom disk. All right, I have to also figure out the flux on the disk, add those two together. Again, there's a reason I'm doing this, is because we're going to do divergence theorem next time, which works with a closed surface, and we want to compare answers. So now we're going to get the flux through the bottom surface. That's that disk at the bottom. Bless you.
Thank you.
We're going to pick the simplest normal vector there is to something that lies in the xy plane. 0, 0, -1. It's a nice, easy normal vector to anything that lies in the normal plane. So that's my normal vector. That gets dotted with the vector field. So I just get the negative z squared. But remember, we're in the xy plane. Z is equal to 0. So it turns out that the flux integral of the disk at the bottom is 0. All right. There's nothing going, there's either nothing going through that surface, or there's as much going in of it as there is out of it. We don't care. It's 0. All right. Since we got 0 for the integrand, we already know none of it's going through. So our flux integral comes out to be 11 pi over 6. We're going to redo this one with divergence theorem on Thursday, and we're going to see if we get that same answer, 11 pi over 6. Okay, questions about that? Here's what I want you to take from that. Not that you have to memorize everything I just did, but that what you saw was, hey, that's the exact same thing we did in a previous problem. We parameterized the top half of the sphere. We found the partials. We did the cross product. We substituted the parameterization into our vector field. We dot product those together to get our integrand, and our limits were our limits for our parameterization. The rest was computing the integral, which could be messy, but that's why we have access to the technology. Let's do this one as a function. Okay. So if I were to do this as a function, let me just, I'm looking at x squared plus y squared plus z squared equals 1. Well, if I'm looking at this as a function, I can do this because I'm only looking at the top half. Okay, so that's basically our function. So when I go to find that normal vector, this f of basically the same thing we did here, I'll subtract the z off. So 1 minus x squared, square root of 1 minus x squared minus y squared minus z. Okay. Now, obviously, when we do the partials of this, it'll get a little messy. So let's let Maple do that for us. But again, my goal is for you to see, hey, we're doing the same thing we did before. Also, we're doing the top half of a sphere. So once again, our region in the xy plane is a circle of radius 1. So the limits will be the same as the limits we had in the previous problem. So let's talk through this. All right, I put in my vector field. Now I put in the function as a function, put in my function as a function of x, y, and z. So basically what I do is I first make it z equals. Then I subtract the z over to the other side to make it a function of x, y, and z. We did this way back when we did gradient as a way of finding a normal vector to a surface. That's all we're doing. So that's it. I'm going to find that gradient. Yes, it is a little bit messy. We could have done it by hand, but we don't need to. Now look, my z component is negative, right? We wanted the z component to be positive, so I'm going to swap the sign on it. And now I don't have to do any conversions. I'm dotting f with this with this gradient. All right, that is my integrand, except we don't want to have z in there. So what do? We say, oh, z is equal to square root of 1 minus x squared minus y squared. we sub that in for any z's that are still in there. All right, so that z got this substituted in. Yeah, Andrew.
So when you switch the z, when you want to switch the sign of the z to positive, you have to switch everything else as well.
Yes.
Okay.
For the normal vector, yeah. Because what we're doing is we're basically taking the normal vector that's pointing up and making it point down.
Okay.
So we switch all the signs.
Gotcha.
So now we got everything in terms of x and y. Now, our region's a circle. We see a whole bunch of x squareds plus y squareds in there. So if we were having to do this by hand, polar, yeah, this would be polar all the way. But Maple should be able to handle this one. It might be a little slow because it's not pretty, but we know what we should get, right? Yeah, still thinking. So again, this is another one that we could have done either way. All right. So a lot of them you can do either way. Parameterization is great because if you can find the parameterization at the beginning, you can plot it in something like Calcplot 3D. As long as it looks like what you want it to look like, you know your parameterization is correct and your limits are correct. You basically just go step, 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 set up your integral and calculate. These aren't that much worse, but obviously there was a little bit of finagling we have to do because, you know, we've got a function in terms of x and y. Well, we've got to make it, you know, a function of x, y, and z to find the normal vector. And then we have to substitute out any z's before we can integrate. And then we do have to think about what our region of integration is. Which one's easier? It's going to depend on the surface and the function the surface and the vector field. All right. So last thing I want to say, you know, the first the first two examples were surface area. The next two examples were surface integrals of a function over a surface. The last three examples were of a vector field over a surface. Okay. So we have three things kind of all simultaneously going on. I just want you to cognitively be aware, and they kind of layered on each other. Each one was like a step up from the one before. Questions at this point?